Picture this: a universe so young, so raw, that not even the first galaxies had taken shape. Yet in this primordial darkness, something remarkable might have already been stirring. Tiny, dense worlds, planets could have been forming in the cosmic shadows, eons before the majestic spirals and clusters we know today. This isn't science fiction. It's one of the most heated debates in modern astronomy. Did the first planets come before the first galaxies? Think about how we've always imagined the story of the cosmos. Galaxies came first, right? Vast clouds of gas and dust collapsing into swirling cities of stars, with planets as mere afterthoughts, tiny specks orbiting their suns. But what if that's not how it happened? What if, in the extreme conditions of the early universe, planets could have emerged first, defying the timeline we've taken for granted? The implications are staggering. It would mean rewriting the very origins of structure in the universe, challenging textbooks, upending theories, and forcing us to rethink how everything from black holes to life itself might have gotten its start. This is the mystery we're diving into today. A mystery that takes us back to a time when the universe was less than 100 million years old, a mere blink in cosmic terms. We're talking about temperatures so intense, pressures so crushing, that matter behaved in ways we can barely simulate. And yet, some scientists believe that in this chaos, the seeds of planets could have taken root. Imagine worlds orbiting not stars, but floating freely in the darkness, forged in the aftermath of the Big Bang itself. How could such a thing be possible? And if it's true, what does that mean for our search for life, for understanding our place in the cosmos? Strap in, because we're about to journey to the very edge of what we know and beyond. To understand just how radical this idea of early planets really is, we need to revisit the cosmic timeline as we've known it. The prevailing theory, what scientists call the lambda CDM model, paints a very specific picture of how structure emerged in our universe. It all begins with dark matter, that mysterious invisible substance that makes up most of the universe's mass. In the early cosmos, dark matter formed vast web-like structures, and where these threads crossed, dense knots called halos began pulling in ordinary matter through gravity. These halos became the nurseries for the first proto-galaxies, swirling pools of hydrogen and helium gas that would eventually ignite with the first generations of stars. Now here's where planets traditionally enter the story much later. According to standard models, planets can't form until after stars have lived and died. Why? Because planets need heavy elements: carbon, silicon, iron, all forged in the nuclear furnaces of stars and scattered through space by supernova explosions. Without these stellar factories creating the raw materials, planetary building blocks simply wouldn't exist. So in this view, the first true planets had to wait billions of years, forming from dusty disks around mature stars, just like our own solar system did 4.6 billion years ago. But what if that assumption is wrong? Some researchers are now proposing that under the extreme conditions of the early universe, tiny, dense objects resembling planets could have formed directly from collapsing pockets of primordial gas, no stars required. These wouldn't be planets as we know them today, but something far stranger: dark, isolated worlds born in an epoch before starlight even filled the cosmos. The implications would reshape not just our understanding of planet formation, but the entire sequence of how structure emerged in the universe. Imagine rewinding the cosmic clock to a time so early that the first stars were still just theoretical possibilities. The universe was smaller, hotter, and far more chaotic. Matter hadn't yet settled into the elegant structures we see today. Yet in this turbulence, some theorists argue that density fluctuations in the primordial gas could have created regions dense enough to collapse under their own gravity, not into stars, but into planet-sized objects. These wouldn't be rocky worlds like Earth or gas giants like Jupiter. They'd be something entirely alien, composed mostly of hydrogen and helium, perhaps with exotic forms of matter we've never observed. The key question becomes, how could these early protoplanets survive in such a violent environment? The young universe was a battlefield of intense radiation, searing temperatures, and cataclysmic shocks from the first collapsing gas clouds. Yet if even a fraction of these objects endured, they might have played a hidden role in shaping the cosmos we see today. Some could have served as seeds for later star formation, or even influenced how galaxies took shape. Others might still be drifting in the darkness between stars, ancient relics from a time before galaxies even existed. This isn't just idle speculation. Observations from the James Webb Space Telescope are already challenging our timelines, spotting galaxies that look suspiciously mature for their young age. If galaxies formed faster than we thought, might planets have beaten them to the cosmic stage? The answers could rewrite not just astronomy textbooks, but our very understanding of how complexity arises in the universe. The notion that planets could have existed before galaxies isn't just a wild hypothesis, it's a possibility gaining traction thanks to cutting-edge research. In 2022, a team studying the Virgo cluster made a startling discovery: a population of so-called free-floating planets drifting untethered to any star. These rogue worlds, some as small as Mars, others rivaling Jupiter in mass, weren't just floating freely, they were far more abundant than anyone predicted. And here's the kicker: their origins remain a mystery. Could some of these lonely wanderers be relics from an era before galaxies even assembled? The idea might sound outlandish, but when you look closely at the physics of the early universe, the pieces start falling into place. Take the James Webb Space Telescope's recent observations. It's spotting galaxies from the universe's first few hundred million years that look shockingly mature, fully formed with intricate structures, as if they've aged far faster than our models predicted. If galaxies grew up quicker than we thought, why not planets too? The extreme density of the early cosmos created environments where matter could collapse into clumps far more efficiently than today. Under those conditions, pockets of gas might have bypassed the star-forming stage entirely, condensing directly into planet-like objects. Picture a universe where these primordial planets acted as gravitational anchors, pulling in surrounding gas and dark matter, effectively laying the groundwork for the first protogalaxies. Critics argue that without heavy elements from supernova, these early objects wouldn't resemble planets as we know them. But proponents counter that they might have been something else entirely: exotic hybrids of hydrogen, helium, and perhaps even dark matter with properties we've yet to imagine. Simulations show that in the absence of heavy elements, gravitational instabilities could still produce dense, compact objects, albeit with bizarre compositions. Some might have been temporary, evaporating under the universe's relentless radiation, while others could have persisted, lurking in the cosmic shadows for billions of years. The debate hinges on a deeper question: how flexible is the universe's recipe for building structures? We've long assumed a linear path: dark matter halos, then gas, then stars, and finally planets. But what if it's messier, more improvisational? The early cosmos was a laboratory of extremes where rules we take for granted might not apply. If planets did form first, they wouldn't just be curiosities, they'd be cosmic pioneers, shaping the evolution of everything that followed. Their gravity could have accelerated star formation, or even influenced the distribution of dark matter, leaving fingerprints we're only now learning to decode. This isn't just academic speculation. If primordial planets existed, they'd rewrite the story of how cosmic ingredients came together. The James Webb Telescope, with its unprecedented sensitivity, might soon uncover clues: anomalies in the infrared glow of early galaxies, or rogue objects drifting in voids where no star has ever shone. Every new observation chips away at the old narrative, leaving us with a thrilling uncertainty. One thing's certain: the universe's childhood was far stranger than we ever imagined. Let's break down these mind-bending theories one by one, starting with the idea that planets could have formed directly from collapsing gas pockets in the cosmic dark ages. Picture the universe before the first stars, a pitch-black expanse filled with swirling hydrogen and helium. In certain regions, the gas wasn't perfectly smooth. Tiny density fluctuations left over from the Big Bang created pockets where matter clumped together more tightly. Under the right conditions, these overdense regions could have collapsed under their own gravity. But here's the twist: without heavy elements to radiate away heat, the gas couldn't fragment into stars like it does today. Instead, simulations suggest entire clouds might have shrunk into planet-sized blobs, dark, hydrogen-rich worlds born in the absence of starlight. Some could have been as massive as Jupiter, glowing faintly from the energy of their slow contraction, drifting through the void like ghostly precursors to everything we know. Then there's the wild card, the remnants of population 3 stars. These were the universe's very first stars, behemoths made purely of hydrogen and helium, hundreds of times more massive than our Sun. They lived fast, died young, and exploded in supernovae so violent they scattered the first heavy elements across space. But here's the provocative thought: what if not all of them vanished completely? Some theorists argue that the cores of these stars, instead of collapsing into black holes, could have cooled and fragmented into dense, planet-like objects. Imagine the leftover heart of a primordial giant, no longer burning, but still massive enough to hold itself together, a cinder world forged in the death throes of the first starlight. These relics might have been rich in exotic states of matter, or even trapped dark matter in their cores, making them utterly unlike anything in our modern cosmos. Finally, consider the cosmic filaments, the gigantic threads of dark matter and gas that wove the universe's large-scale structure. In the early epochs, these filaments weren't just smooth rivers of matter. They were turbulent, prone to knots and kinks where gravity could run amok. Some models show that where filaments crossed or twisted, the sheer weight of accumulating gas could trigger localized collapses, forming planet-mass objects like beads on a string. Unlike the orderly planet formation we see in disks around stars, this would have been a chaotic process, primordial worlds spitting out along these cosmic highways, some ejected into the void, others merging into larger structures that eventually birthed the first galaxies. What ties these theories together is sheer audacity. They force us to rethink how complexity emerges in the universe. Maybe planets weren't just latecomers to the cosmic party. Maybe they were there all along, hidden architects shaping the universe from the shadows. And if even one of these mechanisms is real, the implications are staggering. It would mean planets aren't just byproducts of stars and galaxies. They could be fundamental players in the story of how our universe grew up. The James Webb Telescope might soon give us clues, hunting for infrared signatures of these ancient objects or mapping the distribution of rogue planets in deep space. Until then, the mystery lingers. Were planets the universe's first builders, quietly laying the groundwork for everything that followed? Dark matter has always been the universe's silent architect, its invisible hand shaping galaxies, bending light, and weaving the cosmic web. But what if its role was even stranger? What if certain forms of dark matter didn't just lay the groundwork for galaxies, but actively accelerated the birth of planets in the universe's infancy? This is where the conventional story takes a radical turn. Enter fuzzy dark matter, a hypothetical variant that doesn't behave like the cold, sluggish particles we usually imagine. Instead, it's wave-like, rippling across the cosmos with quantum fuzziness that could have created tiny, dense pockets of gravity, perfect nurseries for planet-sized objects long before stars began to shine. Dr. Annika Peters' groundbreaking simulations in 2023 revealed something astonishing. Under fuzzy dark matter's rules, those primordial density fluctuations, the ones we thought were too smooth to form anything substantial, could have fragmented into clumps with masses comparable to planets. Picture this, a universe still in its dark ages, no starlight yet piercing the void, but already teeming with invisible islands of matter so dense they could pull in gas and dust, collapsing into compact spheres. These wouldn't be planets as we know them today. They'd be something far more exotic, dark matter-anchored objects, their cores humming with particles we've never detected, their gravity sculpting the first structures in the cosmos. Here's why this changes everything. In standard models, dark matter's gravity is like a slow, steady hand gently pulling gas into halos over billions of years. But fuzzy dark matter introduces chaos into the mix. Its wave-like nature means it could have formed unpredictable peaks and troughs in the early universe's density, like ripples in a pond frozen in time. Where those peaks overlapped, matter could have collapsed fast, skipping the gradual buildup needed for galaxies and jumping straight to planet-scale fragments. Some of these fragments might have evaporated as the universe expanded, but others, especially those nestled in the deepest gravitational wells, could have survived, becoming the universe's first solid bodies. Critics argue that without stars to forge heavy elements, these objects wouldn't resemble the rocky or gaseous planets we're familiar with, but supporters counter that they might have been something else entirely, dark matter hybrids, their physics governed by rules we're only beginning to uncover. Imagine a world where the core isn't molten iron but a swirling vortex of invisible particles, its atmosphere pure primordial hydrogen, so dense it behaves more like a liquid than a gas. Such objects wouldn't just be curiosities, they'd be time capsules preserving the conditions of the universe's first moments in ways no star or galaxy ever could. The implications ripple outward. If fuzzy dark matter enabled early planet formation, those objects could have acted as gravitational seeds, pulling in streams of gas and speeding up the birth of the first stars. They might even explain why some ancient galaxies spotted by the James Webb Telescope look oddly mature for their age, because planets, not just stars, were their first, laying the invisible scaffolding. It's a dizzying thought that the universe's smallest structures might have shaped its largest, that planets could have been the hidden architects of cosmic evolution. And if we're right, the proof might be hiding in the faint distortions of distant starlight or in the whisper of a dark matter particle we've yet to catch. The story of planet formation has always been written in metals, not the shiny kind you find in jewelry, but the cosmic definition, any element heavier than helium. Carbon, oxygen, silicon, iron, these are the building blocks of rocky worlds, the seeds of atmospheres, and the raw materials for everything from mountain ranges to ocean beds. Without them, planets as we know them simply couldn't exist. That's why the textbook timeline assumes planets had to wait for generations of stars to live, die, and scatter their metallic ashes across the cosmos. But what if the universe didn't follow the rules? Recent studies of distant quasars, the blazing cores of ancient galaxies, have uncovered something startling. Their light, traveling for billions of years to reach us, carries fingerprints of heavy elements in gas clouds dating back to a mere 700 million years after the Big Bang. That's far earlier than anyone predicted. These absorption lines tell a story of metal enrichment happening at breakneck speed, as if the first stars worked overtime to pollute the cosmos with planet-making ingredients. Here's the puzzle. Traditional models say it should have taken much longer. The first stars, known as Population 3, were giants made purely of hydrogen and helium. When they exploded as supernova, they should have scattered their heavy elements thinly across vast reaches of space. Yet these quasar observations suggest pockets of the early universe were already peppered with metals concentrated enough, perhaps, to jumpstart planet formation long before galaxies reached maturity. Some theorists argue this points to an overlooked chapter in cosmic history, where supernova weren't the only metal factories, one radical possibility. Pair instability, supernova stellar detonations so violent they leave no remnant behind, just a firework of heavy elements flung into the void. these rare, hyper-energetic explosions could have enriched their surroundings far more efficiently than ordinary supernova, creating dense, metal-rich bubbles where protoplanetary clumps might have taken shape. Picture a region of space where the aftermath of such an event left behind a primordial nebula laced with silicon and carbon, its chemistry primed for planet building while the rest of the universe was still a hydrogen-dominated wasteland. But there's another twist. Metals don't just enable planet formation, they accelerate it. In modern star systems, dust grains made of heavy elements act like microscopic chill pills, helping gas clouds shed heat and collapse faster. If pockets of the early universe were metal enriched ahead of schedule, the same physics could have turbocharged the birth of planetesimals, compressing cosmic timelines in ways we're only beginning to grasp. The implications are profound. If metals were abundant earlier than thought, the window for planet formation might have opened wide long before galaxies settled into their familiar shapes. We could be looking at a universe where some planets are far older than the Milky Way, ancient worlds that witnessed the dawn of starlight itself. And with every new quasar spectrum, the evidence grows harder to ignore. The James Webb Space Telescope is now hunting for these chemical fingerprints in even earlier epochs, probing the cosmic dark ages for traces of metals that shouldn't be there. This isn't just about rewriting timelines, it's about reimagining how complexity arises in the universe. Maybe planets didn't patiently wait their turn. Maybe they seized the moment, emerging wherever conditions allowed, their birth catalyzed by the violent, unpredictable chemistry of a young cosmos. The deaths of the first stars weren't just cosmic fireworks, they were the furnaces that forged the very ingredients of worlds. Population 3 stars, those colossal pioneers made of pure hydrogen and helium, burned bright and fast, their lives ending in cataclysms so violent they reshaped the universe. Picture a supernova unlike anything in today's cosmos, a pair instability explosion where the core becomes so hot it spawns particle-antiparticle pairs, destabilizing the star from within. The result, a detonation so complete it leaves no black hole behind, just a blistering shockwave that rips the star apart, flinging newly forged metals into the void. These weren't mere sprinklings of heavy elements, they were tsunamis of carbon, oxygen, and silicon, ejected with enough force to seed vast regions of space far earlier than anyone imagined. Now fast forward to 2024, when astronomers studying GNZ 11, a galaxy so distant we see it, as it was just 400 million years after the Big Bang, found something astonishing. Its light carried the unmistakable signature of carbon-rich dust, a telltale residue of those first stellar explosions. This wasn't just a handful of atoms, it was evidence of rampant metal production happening at breakneck speed. The implications are staggering. If dust, the raw material for planet building, was already plentiful in galaxies like GNZ 11, then the timeline for planet formation doesn't just shift slightly. It shatters. Consider the physics at play. Dust grains are more than debris, they're cosmic glue. In modern star-forming regions, these microscopic particles act as radiators, helping gas clouds cool and collapse into denser clumps. In the early universe, where temperatures were searing and gas was slow to condense, dust could have been the secret ingredient that turbocharged structure formation. A single-pair instability supernova might have littered its surroundings with trillions of graphite and silicate particles, creating pockets where gravity could work its magic faster than ever before. But here's the twist: this wasn't a gradual process. Simulations show that the shock waves from these explosions didn't just scatter metals. They compressed nearby gas into dense, writhing filaments, like cosmic origami folding matter into tight knots. Within these turbulent regions, conditions might have been ripe for dust grains to collide, stick, and grow into pebbles, then boulders, then, just maybe, the seeds of planets. Not in billions of years, but in mere millions, the discovery in GNZ 11 raises a tantalizing question. Could some of these early metal-enriched pockets have bypassed stars entirely, collapsing directly into rogue planets? It's a radical idea, but the math doesn't rule it out. In regions where dust cooled gas rapidly, gravitational instabilities might have spawned planet-mass objects adrift in the darkness, their surfaces bathed not in starlight but in the faint afterglow of the Big Bang. These wouldn't be worlds with familiar landscapes. They'd be soot-black spheres, their atmospheres thick with carbon monoxide and primordial haze, their cores possibly laced with exotic minerals we've never seen. What makes this more than speculation is the James Webb Space Telescope's growing catalogue of ancient galaxies. Each new observation seems to push the boundaries of how quickly structure emerged. If dust, and by extension, planet-building material was widespread just 200 million years after the Big Bang, then the universe's infancy might have been far more industrious than we ever dreamed. The old narrative of stars first, planets later now feels rigid, even naive. In the chaos of the early cosmos, where extremes ruled, perhaps planets didn't wait for permission. They emerged wherever physics allowed, their birth catalyzed by the ashes of the first star's spectacular deaths. Gravitational lensing, one of Einstein's most startling predictions, has become an unexpected tool in the hunt for the universe's loneliest wanderers. When an invisible object drifts across our line of sight to a distant star, its gravity bends the starlight like a lens, creating a fleeting spike in brightness. For decades, surveys like OGLE have used this trick to uncover rogue planets, worlds untethered to any star, drifting through interstellar space by the billions. But here's where it gets eerie. Some of these rogue planets aren't just floating between stars, they've been spotted in the voids between galaxies, far from the dense neighborhoods where planets typically form. Could these isolated objects be relics from an era before galaxies even existed? The math is tantalizing. When OGLE data revealed microlensing events in intergalactic space, the immediate assumption was that these planets had been violently ejected from their home galaxies, flung into the abyss by gravitational slingshots during cosmic collisions. But the numbers don't quite add up. Simulations show that even the most chaotic galactic mergers shouldn't scatter that many planets so far afield. There's another possibility, far more radical. What if some of these wanderers were never part of galaxies to begin with? Picture the early universe again, a time when matter hadn't yet settled into the glittering islands we call galaxies. In that primordial darkness, the first planet-like objects could have formed in isolation, born from collapsing gas pockets or the remnants of population 3 stars. Over billions of years, as galaxies grew around them, these ancient worlds might have avoided capture, left behind like fossils in the cosmic tides. Their very existence would defy the standard narrative, suggesting that planet formation wasn't just a sideshow to galaxy evolution. It might have been a parallel process unfolding in the shadows. The smoking gun could lie in their composition. Planets ejected from mature galaxies would carry the chemical fingerprints of stellar nurseries, traces of heavy elements like iron and silicon. But primordial planets forged before stars polluted the universe should be made almost entirely of hydrogen and helium, with perhaps a whisper of lithium. Unfortunately, microlensing can't yet reveal an object's chemistry. It only tells us the mass and distance. That's where next-generation telescopes like the Nancy Grace Roman Space Telescope come in. With its vastly wider field of view, Roman could detect thousands more rogue planets, mapping their distribution with enough precision to spot anomalies, like a population clustered in regions too empty to explain by ejection alone. The implications ripple beyond astronomy. If even a fraction of these free-floating worlds are primordial, they'd be time capsules from the universe's darkest age, a time before light, before structure, before the rules we take for granted had fully settled into place. Studying them could reveal secrets about dark matter's behavior, the nature of early density fluctuations, and even the conditions that allowed galaxies to eventually form. It's a humbling thought that some of the universe's oldest planets might still be out there, not orbiting stars, not bound to galaxies, but drifting silently through the night, carrying stories older than the Milky Way itself. The way a galaxy takes shape is eerily similar to how planets form. Both start with a swirling disk of material, collapsing under gravity's pull. But here's the cosmic twist. Galaxies were supposed to take billions of years to grow their majestic spirals, while planets were thought to form in mere millions. Now that tidy timeline is being upended by a striking discovery. Some of the earliest proto-galactic disks bear an uncanny resemblance to the swirling nurseries where planets are born, just on a vastly larger scale. Dr. Zujian Shen's team at Princeton noticed something peculiar while simulating the universe's first galaxies. The same gravitational instabilities that clump dust into planetesimals in young star systems also appear to govern how gas fragments in primordial galactic disks just sped up to hyperdrive. Take the classic model of planet formation. In a protoplanetary disk, tiny particles of ice and dust collide, stick together, and gradually snowball into planetesimals, the building blocks of worlds. This process relies on disk instability, where dense patches of material spiral inward, growing denser until gravity takes over. Now zoom way out, to a protogalactic disk, a vast whirlpool of hydrogen and helium gas spanning thousands of light years. Shen's simulations show that under the extreme densities of the early universe, these disks didn't just collapse smoothly into stars. Instead, they fractured into massive, fast-spinning clumps, each potentially weighing as much as a dwarf galaxy. The physics mirrors planet formation, but the scale is staggering. Instead of pebbles coalescing into planets, these were gas clouds the size of solar systems spiraling into galactic cores. Critics argue this is just a coincidence, that the difference in mass and energy makes any comparison meaningless, but Shen's models reveal a tantalizing pattern. Just as planets form faster in denser protoplanetary disks, galaxies might have assembled quicker in regions where the primordial gas was exceptionally thick. In fact, some of the most ancient galaxies observed by the James Webb Telescope show structures that look suspiciously like overgrown versions of planetary birth clouds, lumpy, asymmetrical, and teeming with dense knots. If true, it would mean the universe has a favorite blueprint for building structures, whether they're worlds or galaxies, and that the distinction between small and large might be blurrier than we thought. Dig deeper and the implications get wilder. If protogalactic disks fragmented like protoplanetary ones, then the first galaxies might not have formed from the bottom up, slowly merging smaller pieces, but from the top down, with massive pre-galactic clumps collapsing in one dramatic burst. That could explain why some early galaxies look so mature, their disks already settled and stable when the universe was barely a toddler. It's as if the cosmos hit fast forward, using shortcuts we're only beginning to decode. And if disks at both ends of the size spectrum follow similar rules, the next question is unavoidable. Could planets have been the universe's rough draft, a test run for the grand designs to come? The debate isn't just academic. Understanding which came first, the physics of planets or galaxies, could reshape our search for life. If planetary scale processes helped seed galactic growth, then planets weren't just bystanders in cosmic evolution. They might have been active players, their formation mechanisms writ large across the fabric of the universe. Future telescopes, like the Extremely Large Telescope, could settle the argument by probing the dynamics of ancient disks, hunting for those telltale instabilities. Until then, the great disk debate remains wide open, a reminder that sometimes the universe's most profound patterns hide in plain sight, waiting for us to see the connections. The James Webb Space Telescope has shattered expectations once again, this time with a discovery so bizarre. It's forcing astronomers to question what they thought they knew about the universe's first structures. Deep in the data from Sears 93316, a galaxy observed as it existed just 230 million years after the Big Bang, JWST spotted something that shouldn't be there, a smattering of tiny, ultra-dense objects too compact to be infant galaxies, yet too massive to be ordinary stars. Their infrared signatures suggest they're bloated and cool, like super Jupiters on a cosmic scale, floating in the void long before modern planet formation should have been possible. Reactions in the scientific community range from exhilaration to outright skepticism. Supporters of early planet theories point to the objects' thermal profiles. Their light curves match what you'd expect from gas giants untethered to stars, glowing faintly from residual heat. One compelling interpretation suggests these could be the first direct evidence of primordial planets, formed in the wake of population 3-star explosions and left to wander in the darkness. Critics, however, fire back that the data is being overinterpreted. They argue these objects are more likely to be failed galaxies, stunted proto-galactic fragments that collapsed but never ignited enough stars to shine brightly. The debate hinges on two irreconcilable models. If these objects are planet-like, then their sheer mass challenges every formation mechanism we've theorized. A super Jupiter forming without a star would require gas concentrations far denser than most early universe simulations allow. Yet if they're proto-galaxies, their lack of stellar activity is equally puzzling. Why would gas clumps this massive remain so quiet, so dark? Dr. Catherine Jones's team at Caltech favors a middle ground, what they call hybrid dark objects. Their analysis suggests these enigmas might be a previously unknown class of celestial body. Dark matter-dominated structures wrapped in thick hydrogen shrouds, too cool to form stars but dense enough to mimic planetary infrared signals. It's a wild idea, but it would explain why JWST sees them lurking at the edges of early galaxies like shadowy attendants. The implications ripple far beyond classification. If even a fraction of these objects are rogue planets, it would mean the universe's first worlds weren't just early, they were monstrous, dwarfing anything in our solar system. And if there's something else entirely, well, that would mean we're staring at a cosmic phenomenon nobody predicted, a reminder that the early universe was stranger than our boldest models dared to suggest. Either way, JWST has thrown down the gauntlet, and astronomers are racing to pick it up. Supercomputers have become our time machines, gigantic digital laboratories where we can rewind the cosmos to its infancy and watch the impossible unfold. One of the most ambitious of these virtual experiments is the Renaissance simulation, a staggeringly detailed model that reconstructs the universe's first few hundred million years with unprecedented precision. When researchers ran this simulation, expecting to see the slow, stately dance of gas collapsing into proto-galaxies, they got something far stranger, a cosmic surprise party. Sprinkled along the dense filaments of dark matter and hydrogen, the universe's scaffolding were dozens of clumps with masses up to 10 times that of Earth, condensing like dew on a spider's web. These weren't stars, they weren't galaxies, they were planet-sized objects forming in the voids between the birthplaces of galaxies, far earlier than any textbook predicted. The physics behind this phenomenon is as elegant as it is counterintuitive. In those early filaments where gravity pulled streams of primordial gas into narrow, high-pressure channels, matter didn't behave the way it does today. Without heavy elements to cool the gas efficiently, it couldn't fragment into stars easily, but in the simulation, something unexpected happened: turbulence. As gas rushed along the filaments, it didn't flow smoothly. It churned, creating whirlpools and eddies where density spiked. In these knots, gravity took over, compressing hydrogen and helium into spheres massive enough to resist being torn apart by the universe's expanding fabric. The simulation's verdict, free-floating planets or something resembling them, could have been a natural byproduct of cosmic web dynamics, born from chaos rather than the ordered nurseries of protoplanetary disks. Yet not everyone's convinced. The biggest stumbling block: resolution. Even the most powerful supercomputers can't simulate every atom in the early universe. they rely on approximations, smoothing out details smaller than a certain scale. Critics argue that those 10 Earth mass clumps might just be artifacts of the simulation's pixelated view, like mistaking a blurry photo of a cloud for a UFO. When you're modeling something as vast as the cosmic web, it's easy for numerical shortcuts to create phantom structures that wouldn't exist in reality. But here's where the plot thickens. The Renaissance team ran a battery of tests, tweaking resolution and physics parameters to see if the planet-like objects persisted. Astonishingly, even at higher resolutions where the simulation could track smaller gas fluctuations, the clumps held firm. What's more, their properties matched theoretical predictions for so-called primordial planets, cold, dense, and rich in molecular hydrogen, with atmospheres so thick they'd resemble mini Neptunes more than Earth. If the simulations aren't lying, these objects wouldn't just be curiosities. They'd be gravitational anchors tugging on nearby gas and subtly shaping how galaxies assembled around them. Skeptics counter with another hurdle: survival. The early universe was a battlefield of ultraviolet radiation from the first stars, blasting away fragile hydrogen atmospheres. How could these protoplanets endure? The simulations suggest an answer. Some might have formed in the densest, most shielded heart of filaments, where gas acted like a cosmic insulator. Others could have migrated rapidly into the shadows of larger structures, escaping the brunt of radiation. A fraction might even have cannibalized their neighbors, growing massive enough to hold onto their gassy envelopes despite the chaos. The debate is far from settled, but one thing's clear. If supercomputers are hinting at a hidden population of primordial planets, it's a clue we can't ignore. Upcoming telescopes, like the European Extremely Large Telescope, could hunt for their infrared glow in distant gas clouds. Until then, the Renaissance simulation stands as a provocative glimpse into a universe where planets might have been cosmic pioneers, not afterthoughts, but foundational pieces in the architecture of everything. The standard model of cosmic evolution isn't the only game in town. Alternative cosmologies have been quietly rewriting the rules, and some predict early planet formation not as a fluke, but as a fundamental feature of the universe. Take emergent gravity, a radical framework where gravity isn't an innate force but a side effect of entropy, a kind of cosmic friction emerging from the universe's underlying quantum bits. In this view, the early cosmos wasn't just a smooth soup of particles. It was a seething network of microscopic interactions, and where entropy gradients peaked, gravity-like effects could have spontaneously clumped matter into planet-sized objects before stars or galaxies took shape. Picture a universe where structure doesn't wait for dark matter's slow pull. Itself assembles, like iron filings aligning to an invisible pattern, with planets as its first brushstrokes. Then there's string gas cosmology, a sibling to string theory that swaps the Big Bang for a bouncing universe. Here, the dense, hot early state wasn't a singularity but a tangled web of vibrating strings, their energy driving violent oscillations in spacetime. Dr. Stefan Alexander's pioneering work reveals how these oscillations could have twisted spacetime itself, creating regions of torsion, a spiraling distortion that funnels matter into dense knots. Unlike traditional gravity, torsion doesn't just attract, it twists, spinning gas into compact whirlpools that could collapse directly into planets without needing stars as intermediaries. The math suggests these torsion-driven structures would have been abundant in the universe's first moments, like eddies in a rushing river, their scales determined not by galaxy formation but by the fundamental physics of strings. Critics argue these ideas are too speculative, lacking the observational scaffolding of mainstream cosmology, but supporters counter with a provocative point. If the James Webb Telescope keeps finding ultra-early structures that defy lambda CDM predictions, maybe it's time to entertain wilder possibilities. After all, Einstein's relativity once seemed esoteric too, until it explained Mercury's orbit. The beauty of these alternative models is their testability. Emergent gravity, for instance, predicts subtle differences in how early planets would cluster, while torsion leaves fingerprints in the spin patterns of ancient gas clouds. Upcoming probes like the Square Kilometre Array could hunt for these anomalies, turning philosophical musings into hard data. What unites these theories is a daring premise that planets aren't just byproducts of cosmic evolution, but active participants, even catalysts in how the universe grew up. Whether through entropy, strings, or spacetime's twists, they suggest a cosmos far more inventive than we've dared to imagine, where the first worlds might have been not accidents but inevitabilities. The deeper we look, the clearer it becomes. The universe's childhood was likely stranger than any single theory can capture. And that's what makes this mystery so thrilling. We're not just uncovering answers. We're rewriting the question. The cosmic microwave background, the faint afterglow of the Big Bang, has long been our most pristine window into the universe's infancy. But buried in its near-perfect uniformity are subtle anomalies, whispers of a cosmos far more textured in its youth than we ever imagined. When the Planck satellite mapped this relic radiation with unprecedented precision, it uncovered puzzling cold spots and unexpected swirls in polarization flaws in the cosmic fingerprint that defy standard models of structure formation. One tantalizing interpretation: these imperfections might be scars from a time when the universe was already clumpy, when dense objects like primordial planets or their building blocks cast gravitational shadows on the fledgling cosmos. Dr. Yassin Ali Haimoud's groundbreaking work takes this idea even further. His models reveal how collisions between ancient planetesimals, rocky bodies that never grew into full-fledged worlds, could have left their mark on the CMB in a way we've only just learned to decode. Picture the early universe not as a smooth soup of particles, but as a seething arena where countless kilometer-sized objects smashed together in the darkness. Each collision would have released bursts of energy, heating the surrounding gas and creating localized ripples in the CMB's temperature and polarization. These distortions wouldn't be random, they'd form distinct patterns like fingerprints pressed into the cosmic backdrop. The math is staggering. If just 1% of the universe's early matter clumped into planetesimals before the first galaxies, their collisions would have generated enough energy to alter the CMB's spectrum in ways Planck's instruments might barely detect. Ali Haimoud's team calculated that these events would produce a specific type of distortion called a mu signature, a subtle imbalance in the CMB's blackbody curve caused by energy injections during the cosmic dark ages. While current data isn't yet precise enough to confirm this signal, next-generation observatories like the proposed PIXI mission could have the sensitivity to spot it. A detection wouldn't just hint at early planets, it would revolutionize our understanding of how quickly structure emerged after the Big Bang. Skeptics counter that other phenomena, early black holes or exotic dark matter interactions, could produce similar distortions. But here's what makes the planetesimal hypothesis unique: its testability. If the anomalies align with predictions for collision rates in primordial disks, it would offer a direct window into an era we've never probed before. Imagine confirming that rocky bodies, perhaps even molten protoplanets, were already forming while the universe was still in diapers. It's a humbling thought that the scars of these ancient crashes might still be etched into the sky, waiting for us to read their story. The implications ripple beyond astronomy. If planetesimals existed before galaxies, they could have been cosmic crucibles, forging the first heavy elements through relentless collisions long before supernova took over. Their gravity might have seeded the densest regions where galaxies later blossomed, turning them from bystanders to architects of cosmic evolution. And if we're right, the CMB isn't just a relic, it's a palimpsest, its faintest irregularities hiding clues to a lost chapter in our universe's history. The hunt for these whispers is on, and with every new analysis, we're one step closer to rewriting the story of how it all began. The metallicity paradox cuts to the heart of why early planets seem impossible without heavy elements. How could solid worlds even exist? We've always assumed planets needed metals, those cosmic building blocks forged in stellar furnaces. Yet the deeper we probe the early universe, the more this assumption unravels. Take the case of quasars from the cosmic dawn. Their light reveals pockets of space already laced with carbon and oxygen, when, by all accounts, there hadn't been enough time for generations of stars to produce them. This isn't just a discrepancy, it's a glaring inconsistency in the timeline of cosmic chemistry. Enter one of the boldest solutions, quark nova. These aren't your average stellar explosions. When ultra-dense neutron stars, the collapsed cores of dead suns, undergo a catastrophic transition, they might not just explode, they might unravel, their very protons and neutrons dissolving into a soup of free quarks. The resulting detonation wouldn't just scatter heavy elements, it would forge entirely new forms of matter, ejecting nuggets of strange quark matter alongside torrents of gold, platinum, and uranium. Crucially, these events wouldn't pollute the universe evenly. Like cosmic sprinklers, they'd drench nearby regions with metals while leaving others untouched, creating isolated bubbles where planet formation could ignite prematurely. But the real shocker, some theories suggest these explosions could have birthed an entirely new class of planets. Imagine a chunk of quark matter, a fragment from a quark nova's fury, cooling into a stable, ultra-dense sphere. Such an object wouldn't just contain metals, it might be metal, a world made of condensed quark gluon plasma, its surface harder than diamond, its core governed by quantum rules we barely understand. These quark planets, if they exist, would defy every convention. They'd be indestructible relics of the universe's most violent physics, wandering the cosmos with compositions unlike anything formed in protoplanetary disks. Then there's the dark horse candidate, primordial black holes as planetary seeds. Not the monstrous black holes of today, but microscopic ones, some as light as asteroids, theorized to have formed in the chaos of the early universe. If these tiny gravitational pits existed, they could have acted like cosmic vacuum cleaners, sucking in surrounding hydrogen and helium until they wore thick coats of gas, essentially becoming the cores of planet-like objects. These wouldn't be planets in the traditional sense, but something far stranger. Black hole planets, their hearts a knot of spacetime itself, their outer layers masquerading as ordinary atmospheres. The implications are staggering. If metals could be forged through quark nova, or if planets could form around exotic seeds like primordial black holes, then the metallicity paradox isn't a dead end, it's a doorway. A doorway to a universe where planets didn't wait for stars to die, where the building blocks of worlds came from physics we're only beginning to glimpse. Future telescopes analyzing the spectra of ancient gas clouds might find the smoking gun, patches of space enriched with rare isotopes like plutonium or curium, elements so unstable they must have been freshly minted. Until then, the paradox stands as both a challenge and an invitation to rethink not just how planets form, but what fundamentally they're even made of. Among the most radical ideas in modern cosmology is the concept of dark stars, not the gloomy ballad by Bowie, but hypothetical celestial objects powered not by nuclear fusion, but by the annihilation of dark matter. Proposed by physicist Catherine Fries and her team, these bizarre structures could rewrite the rules of how the universe's first objects formed. Imagine a star that doesn't shine from burning hydrogen, but glows faintly as dark matter particles collide and self-destruct in its core, releasing just enough energy to keep the entire structure puffed up like a cosmic hot air balloon. These wouldn't be stars as we know them. They'd be bloated, diffuse monsters hundreds of times wider than our solar system, yet no hotter than a campfire. But here's where it gets wild. When their dark matter fuel ran out, they wouldn't just fizzle. They might collapse directly into something resembling planets. The physics behind this transformation is as elegant as it is strange. Unlike normal stars, which fight gravity's crush with the outward pressure of fusion, dark stars are balanced on a knife's edge. Their entire structure depends on a steady trickle of energy from dark matter annihilation. Cut off that fuel supply and gravity wins instantly. Without fusion to keep them inflated, these behemoths would implode catastrophically, shedding their outer layers in a whisper-thin wind while their cores compacted into ultra-dense spheres. Simulations suggest the end product could range from Jupiter mass blobs to super-Earths, all forged not from stardust but from the ashes of a dark matter engine. What's even more mind-bending is what these objects would be made of. Lacking heavy elements, they'd consist almost entirely of primordial hydrogen and helium, but compressed under pressures so extreme that the gas might behave unlike anything in our solar system. Some models predict exotic states of matter, like metallic hydrogen cores or helium rain that falls upward under intense magnetic fields. Others speculate that residual dark matter, trapped in the collapse, could give these objects bizarre gravitational quirks, making them wobble or emit faint particle jets as they drift through space. The implications ripple far beyond celestial oddities. If dark stars birthed free-floating planets, they'd be scattered across the early universe like cosmic breadcrumbs, gravity wells that could have attracted gas and jump-started galaxy formation in unexpected places. Some might still be out there today, lurking in interstellar space like fossilized remnants of a forgotten era. The James Webb Space Telescope could hold the key to finding them. While true dark stars would be too dim to spot directly, their planetary descendants might betray their presence by blocking background starlight or emitting subtle heat signatures from their slow contraction. Critics argue it's all speculative, that dark matter's nature is still too poorly understood to bank on such exotic physics, but supporters counter that the universe has surprised us before. After all, if the early cosmos was rich in dark matter, why wouldn't it have crafted structures we've never dreamed of? Whether or not the hypothesis holds, dark stars remind us that the universe's infancy was likely stranger than any textbook could capture, a laboratory where the rules were written in particles we're still struggling to detect. MOA 2011 BLG262 isn't your typical rogue planet. Discovered through microlensing in 2011, this lonely wanderer, possibly orbited by a tiny moon, drifts through the void between stars untethered to any sun. What makes it extraordinary isn't just its isolation, but its motion. Tracking its path across the sky reveals a trajectory so fast and so straight that astronomers began questioning its origins. Most rogue planets are thought to be ejected from their star systems, slingshotted away by gravitational chaos. But MOA's speed and direction don't match that story. Instead, its kinematics suggest something far more intriguing. It might have always been free, born in the darkness long before galaxies finished assembling. Then there's the enigma of SIMP J0, 1365663 plus 09344703, a rogue planet so massive it blurs the line between planet and failed star. Found in 2018, this object races through space with a magnetic field 200 times stronger than Jupiter's, so powerful it generates auroras without a star to fuel them. Its age, roughly 200 million years, far too young to have drifted from a distant star system. The most compelling theory, it might be a refugee from one of the early dwarf galaxies torn apart by the Milky Way's gravity, a planetary castaway from an ancient cosmic collision. Now consider the Vera Rubin Observatory's upcoming legacy survey of space and time, set to map billions of celestial objects with unprecedented precision. Early projections suggest it could detect thousands more rogue planets, some moving so fast they might be intergalactic hitchhikers flung into the void during galaxy mergers. But here's the tantalizing possibility. If even a handful of these drifters exhibit trajectories or compositions inconsistent with ejection models, it could point to a primordial origin. Imagine worlds that never knew a star, forged in the turbulence of the universe's first gas clouds and flung into eternity before the first galaxies ignited. The key to unraveling this mystery lies in metallicity. Planets ejected from mature star systems carry the chemical fingerprints of stellar nurseries, traces of iron, silicates, and carbon. But true primordial planets born from pristine hydrogen and helium would be nearly metal-free, their compositions betraying their ancient birthright. Upcoming spectroscopy from the Rubin Observatory and JWST could finally settle the debate, analyzing the faint infrared glow of rogue atmospheres for telltale signs of youth or antiquity. The implications are staggering. If even one rogue planet is confirmed as pre-galactic, it would rewrite the cosmic timeline, proving that planets didn't just follow structure, they pioneered it. These wanderers might not be orphans after all, but relics of a time when the universe was still figuring out how to build itself. And with every new detection, we edge closer to answering the ultimate question. Were planets the universe's first children, born in the dark before the stars woke up? What if the seeds of planets weren't forged in fire, but woven into the fabric of spacetime itself? Among the most daring theories in cosmology is the idea that some worlds, especially the earliest ones, might be cosmic relics of quantum fluctuations frozen in time. Picture the universe in its first trillionth of a second, a realm where quantum uncertainty ruled supreme. Here, tiny fluctuations in energy flickered in and out of existence, most vanishing as quickly as they appeared. But according to Dr. Laura Mersini-Horton's calculations, a rare few could have been stretched to planetary scales during inflation, the universe's explosive initial expansion. These wouldn't be mere density ripples, they'd be fossils, quantum probabilities amplified to macroscopic reality. The math behind this is as elegant as it is mind-bending. Inflation didn't just stretch space, it stretched the quantum fluctuations embedded within it, transforming microscopic blips into continent-sized wrinkles in matter distribution. Most smoothed out as the universe evolved, but Mersini-Horton's models suggest an intriguing exception. Particularly intense peaks in the quantum probability field might have resisted dissipation, collapsing under their own gravity into stable, planet-sized objects. These wouldn't form through conventional accretion or disk dynamics. They'd emerge fully formed, like cosmic déjà vu, their existence preordained by the quirks of quantum statistics. Critics argue the idea veers into metaphysics. After all, how does a probability peak become tangible matter? The answer lies in the interplay between quantum mechanics and gravity. During inflation, regions with slightly higher energy density, those statistical outliers curved spacetime more sharply around them. As inflation ended, these warped zones preferentially attracted matter, acting like gravitational seeds. Over time, gas and dust would have funneled into these pre-existing wells, creating objects that looked like planets but carried the imprint of primordial quantumness in their cores. Simulations show these fluctuation fossils would cluster in predictable patterns, their distribution mirroring the statistical noise of the early universe rather than the structured hierarchies of galaxies. What would such an object look like? Unlike planets born from stellar nurseries, quantum relics might lack conventional differentiation, no iron cores or silicate mantles. Instead, their internal structure could reflect the original fluctuation's geometry, with layered densities frozen like a snapshot of spacetime's earliest shivers. Some might even exhibit bizarre gravitational anomalies, their mass not perfectly centered due to the asymmetric nature of their quantum origins. The implications are staggering. If even a handful of rogue planets bear these signatures, they'd be direct windows into the pre-inflationary universe time capsules encoding data no telescope could otherwise glimpse. Future missions like LISA, the Gravitational Wave Observatory, might detect the ripples from their formation, while next-generation telescopes could hunt for their unique infrared or kinematic fingerprints. It's a long shot, but as Mercini Horton herself puts it, the universe loves recycling. Why not recycle its quantum noise into something as enduring as a planet? Whether the theory holds or not, it's a reminder that the cosmos has never been shy about defying our neat categories, and that the line between quantum ghost and tangible world might be thinner than we ever dreamed. Black holes and planets might seem like cosmic opposites, one a devourer of light, the other a potential cradle for life. But what if the birth of the first planets indirectly spawned some of the universe's earliest black holes? Dr. Priyamvada Natarajan's groundbreaking work reveals a startling possibility. Dense clusters of primordial planets could have collapsed into the elusive seeds of intermediate mass black holes, those enigmatic middleweights between stellar remnants and supermassive giants. Picture a swarm of hydrogen-rich protoplanets, each several times more massive than Jupiter, drifting in the darkness before galaxies fully formed. Without stars to anchor them, these free-floating worlds would huddle together in tight knots drawn by their combined gravity. But in the early universe's extreme density, such clusters wouldn't stay stable for long. Natarajan's simulations show how gravitational interactions could send these planets spiraling inward, colliding and merging in a chaotic dance. Over time, the cluster's core would grow denser and hotter until, critically, the combined mass crossed a threshold where gravity overwhelmed all other forces. The result, a catastrophic implosion, not into a star, but directly into a black hole with hundreds or even thousands of solar masses. This process elegantly solves two cosmic puzzles at once. First, it explains how intermediate mass black holes like the one recently detected in the Andromeda Galaxy could exist so early in the universe, long before successive galaxy mergers built up supermassive behemoths. Second, it offers a plausible origin for rogue planets spotted in modern surveys, survivors ejected from these clusters just before the final collapse. The math reveals a Goldilocks scenario. If the initial cluster contained between 50 to 1,000 protoplanets, their mergers could skip the star stage entirely, funneling enough mass into a small enough volume to birth a black hole outright. Critics argue this demands too perfect a storm of conditions. Why wouldn't the cluster just form stars instead? Natarajan's models counter that in metal-free environments, cooling mechanisms were too inefficient for star formation. Without heavy elements to radiate away heat, collapsing gas couldn't fragment into stars efficiently, leaving planet mergers as the only path to compactness. Supporting this, observations of modern globular clusters, dense stellar cities where intermediate mass black holes lurk, show they often harbor disproportionate numbers of rogue planets, like cosmic breadcrumbs pointing to a violent past. The implications stretch beyond black hole origins. If protoplanets were this abundant in the early universe, their gravitational tugs might have shaped the distribution of dark matter, funneling it into filaments that later birthed galaxies. Some could even persist today, ancient, frozen worlds orbiting the very black holes they helped create, their surfaces scoured by eons of tidal forces and radiation. The James Webb Telescope might soon spot these survivors by their faint heat signatures near active galactic cores. This isn't just about rewriting cosmic history, it's about recognizing planets as potential architects of the universe's darkest structures. From cradle to collapse, their story might be far grander and far stranger than we ever imagined. Hidden in the faint whispers of hydrogen atoms lies one of our most promising tools to hunt for the universe's oldest worlds, the 21-centimeter line. This subtle signal, emitted when the spin of a hydrogen atom's electron flips, paints an invisible map of the cosmos's primordial gas. But it's not just a relic of the past, it's a cosmic detective, capable of revealing shadows cast by objects too dim to see directly. When the first planets emerged, they didn't just sit in the darkness, they sculpted it, absorbing and distorting the 21-centimeter radiation passing through them. Future telescopes like the Primordial Project's massive arrays aim to decode these distortions, turning static into stories. The key lies in what astronomers call the 21-centimeter forest, an intricate web of absorption lines imprinted on background radio waves by patches of neutral hydrogen. Just as sunlight filtering through a dense forest leaves dappled shadows on the ground, 21-centimeter radiation passing through the early universe carries fingerprints of every dense object it encountered. Planets, even those without stars, would leave distinct notches in this signal. Their gravity would pull nearby hydrogen into thicker shells, creating deeper absorption dips, while their own hydrogen atmospheres would add extra layers of interference. The result, a unique spectral signature, like a barcode revealing a world's mass, temperature, and even orbital velocity, if it happened to be drifting through a filament of primordial gas. Primordial, slated to begin observations in the next decade, isn't just another radio array, it's a time machine tuned to the universe's darkest age. With thousands of antennas spread across remote deserts, it'll capture the 21-centimeter signal with unprecedented sensitivity, hunting for anomalies that other telescopes blur into noise. The project's lead theorist, Dr. Hamsa Padmanabhan, compares it to listening for raindrops in a thunderstorm. The cosmic dawn's hydrogen emission is the storm, she explains, but hidden in that roar are the tiny, sharp clicks of absorption, each one potentially a planet-sized object we've never seen. What makes this approach revolutionary isn't just its precision, but its range. While optical telescopes like JWST peer at bright galaxies, primordial can probe the voids between them, the very regions where rogue planets would have drifted unimpeded. A single detection could rewrite our understanding of structure formation. Imagine spotting a Jupiter mass object's fingerprint in gas clouds from just 200 million years after the Big Bang. It wouldn't just confirm early planet formation, it'd expose an entire invisible population lurking where no telescope has thought to look. The challenges are staggering. The 21-centimeter signal from the cosmic dawn is faint, stretched by the universe's expansion to wavelengths of several meters, and drowned in radio interference from Earth and the Milky Way. Primordial team is developing AI-driven algorithms to sift through petabytes of data, isolating the delicate patterns of absorption that might betray a planet's presence. Even then, false positives abound. Turbulent gas clouds or primordial black holes could mimic some signatures. That's why the project plans to cross-reference hits with gravitational lensing surveys, looking for objects whose mass and position align in both datasets. If successful, this technique could unveil a hidden chapter of cosmic history. Planets might not just be debris from galaxy formation. They could be the universe's first solid structures, their subtle tugs on hydrogen gas shaping how later galaxies assembled. And the data won't stop at detection. The depth and shape of absorption lines could reveal atmospheric composition. A primordial planet's hydrogen envelope, untouched by metal pollution, would absorb 21-centimeter radiation differently than one enriched by later supernova. Some models even suggest that magnetic fields from these early worlds could polarize the signal, leaving twists in the data that betray their presence. The implications stretch beyond astronomy. If 21-centimeter forests reveal a trove of free-floating planets, it would suggest that planet formation isn't just a byproduct of stars. It's a fundamental process the universe employs to organize matter, as essential as galaxy formation. Primordial first light is still years away, but when it flickers on, we might finally glimpse the universe's forgotten children, worlds born in the dark, waiting to tell their stories. Deep in the globular cluster Messier 4, orbiting a pair of long-dead stars, drifts a relic older than Earth itself, the exoplanet PSRB 1620-26b. Nicknamed Methuselah, this ancient world is estimated to be nearly 13 billion years old, making it one of the first planets ever born in our universe. Its very existence is a cosmic puzzle. How could a planet form so early, when the cosmos was still a near-sterile expanse of hydrogen and helium? the answer might lie not in how it looks today, but in what it carries from its violent birth. This is exoplanet archaeology, the art of decoding planetary fossils to uncover the universe's formative years. Dr. Lisa Kaltenegger, director of the Carl Sagan Institute, has pioneered techniques to probe these primordial worlds for chemical scars. Her studies focus on the concept of pollution, the subtle contamination of a star's atmosphere by heavy elements from consumed planets. When a planet like Methuselah spirals into its host star, it leaves behind a spectral smear of metals like ink bleeding into water. But in PSRB 1620-26b's case, the contamination is reversed. The white dwarf and pulsar it orbits are too dense to absorb material, preserving the planet's original chemistry like a fly in amber. If we could sample its atmosphere, we'd glimpse a recipe from the universe's first kitchen, a volatile mix of hydrogen, helium, and perhaps traces of lithium forged minutes after the Big Bang. The real breakthrough came when Kaltenegger's team modeled the atmospheric spectra of hypothetical first-generation planets, worlds born before supernova enriched the cosmos with metals. Without carbon or oxygen to form clouds, their skies would be eerily transparent, their heat trapped not by greenhouse gases but by the sheer density of primordial hydrogen pressing down like a cosmic blanket. Some might have helium rainstorms condensing in upper layers and falling as glowing droplets. Others could exhibit supersonic winds, their atmospheres churning violently under intense stellar radiation from the universe's earliest, hottest stars. These aren't just academic exercises, they're field guides for telescopes like JWST, which could soon spot similar worlds by their unique infrared fingerprints. The hunt extends beyond Methuselah. In 2023, astronomers identified a candidate in the Milky Way's halo, a rogue planet with an orbit suggesting it was captured from a dwarf galaxy older than our own. Its trajectory hints at an origin in the cosmic dawn, a survivor of galactic cannibalism. Kaltenegger's models suggest such worlds might be time capsules, their interiors preserving layered records of early accretion. Imagine drilling through their crust to find not silicate rock, but exotic ices of nitrogen or methane, frozen into strange crystalline forms under pressures unseen in modern star systems. Critics argue these ancient planets are too rare to study meaningfully, that their survival against 13 billion years of cosmic violence makes them statistical flukes. But supporters counter that their rarity is precisely why they matter. Like uncovering a single dinosaur feather that rewrites evolutionary biology, one primordial planet could upend our entire narrative of cosmic evolution. The upcoming extremely large telescope with its 39-meter mirror could finally resolve these debates, analyzing the reflected light from rogue planets to detect atmospheric compositions untouched by stellar processing. This isn't just about rewriting history books, it's about recognizing that planets might be the universe's most persistent artifacts. Civilizations rise and fall, stars burn out, galaxies collide, but some worlds endure, carrying whispers from an era before time had meaning. And with every new observation, we're learning to listen. Time isn't just a ticking clock in cosmology, it's a fluid, stretchable fabric that warps our most basic intuition about first and before. Picture the early universe not as a linear sequence, but as a rapidly inflating balloon where events unfolded at vastly different rates across space. A single cosmic moment near the Big Bang could have lasted long enough for planets to form in one region while galaxies hadn't even begun taking shape in another. This is the heart of the dilemma. When we ask whether planets preceded galaxies, we're assuming a universal timeline that simply didn't exist. Dr. Sean Carroll, a leading theoretical physicist, frames this beautifully. In an expanding universe, first is a local phenomenon, not a global decree. His work highlights how inflation, the universe's explosive early growth, created pockets where time effectively flowed at different speeds. A dense knot of matter could experience billions of years of local time while the broader universe remained in its cosmic infancy. In such regions, gravitational collapse might have raced ahead, forming planet-sized objects long before the average cosmic density allowed for galaxy-scale structures. This challenges our Earth-bound intuition that time progresses uniformly everywhere. Think of it like weather systems on Earth. While one continent bakes in midday sun, another sleeps under midnight stars. Similarly, the early universe had its own time zones, where physical processes could sprint or crawl depending on the energy landscape. A planet-forming event in one of these hotspots might have been contemporaneous with pristine gas clouds elsewhere, not older in an absolute sense, just further along its local evolutionary path. The implications ripple through every theory about early structure formation. If time dilation allowed some regions to forge planets while others lingered in primordial chaos, then the very notion of a cosmic sequence collapses. We can't simply line up events like beads on a string. We need a four-dimensional map that accounts for relativity's wrinkles. This might explain why the James Webb Telescope keeps finding mature galaxies alongside seemingly primordial gas clouds in the same observational slice. They're not contradictions, but reflections of time's fluidity. Critics argue this complicates things unnecessarily, that Occam's razor favors a single timeline, but Carroll counters that the math doesn't lie. Inflation's quantum fluctuations would have naturally created density variations large enough to distort local time flow. Supporting this, simulations at the Perimeter Institute show how these time warps could persist long enough to allow for isolated episodes of planet formation. The smoking gun, certain isotopic ratios in ancient meteorites, which suggest pockets of rapid nucleosynthesis inconsistent with a uniform early universe. Here's where it gets truly mind-bending. If time was this malleable, some of the first planets might not just be old, they could be older than the universe itself when measured by their local clocks. Like a hiker taking a shortcut through a mountain while others circle the base, these worlds would have experienced more ticks of time than the cosmic average. This isn't science fiction, it's relativity in action. The challenge for cosmologists is learning to read these scrambled timelines, assembling a story where first becomes as much about place as it is about time. The takeaway is humbling. Our language lacks the vocabulary to describe a reality where before and after depend on where you're standing. Yet this very complexity might hold the key to unlocking the universe's deepest mysteries, not by simplifying them, but by embracing their beautiful, tangled nature. Imagine cracking the universe's oldest cold case by bringing together the ultimate detective team, each with a unique set of skills no single instrument could match. That's the power of multi-messenger astronomy, and by the 2030s, we'll have the tools to combine gravitational waves, neutrino whispers, and infrared starlight like never before. The key lies in synergy. LISA, the space-based gravitational wave observatory, will sense the ripples from colliding primordial black holes. Hypercamioc colossal water tank will catch neutrinos from the explosive deaths of the first stars, and JWST piercing infrared gaze will map the aftermath of these ancient cataclysms. Together, they'll form an intergalactic net trapping clues about whether planets or galaxies came first. Take gravitational waves first. LISA trio of spacecraft floating millions of kilometers apart will detect low-frequency ripples from mergers too ancient and massive for Earth-based observatories to spot. If intermediate mass black holes, those potential offspring of collapsed planet clusters, lurk in the early universe, their collisions would vibrate spacetime with a signature only LISA can catch. But gravitational waves alone are like hearing an explosion in the dark. You know something happened, but not what caused it. That's where hypercamioc comes in. When the first stars died as supernova or quark nova, their cores blasted out neutrinos, ghostly particles that travel nearly unimpeded across cosmic distances. By timing these neutrino bursts against LISA wave detections, we could pinpoint violent events where heavy elements were forged, seeding planet formation far earlier than expected. Yet even this duo has blind spots. Enter JWST, the cosmic archaeologist. Its infrared vision can peer back to epochs where the ultraviolet light of early stars has been stretched by the universe's expansion into infrared wavelengths. But more crucially, JWST can analyze the chemical fingerprints in ancient gas clouds' metals from those first supernovae and correlate them with LISA and Hyper-Kamiokande data. Picture this trifecta in action. LISA feels a ripple from a 12-billion-year-old black hole merger, Hyper-Kamiokande, and catches a neutrino pulse from the same patch of sky milliseconds later. JWST then zooms in to find a galaxy there, its gas laced with platinum and gold. That chain of evidence would suggest stars lived, died, and enriched space with planet-building materials shockingly fast potentially before galaxies fully coalesced. The real magic happens when these datasets overlap. Gravitational waves reveal the dynamics of unseen massive objects. Neutrinos expose the energy of stellar explosions, and JWST documents the chemical fallout. Cross-referencing them could solve puzzles like the quark-nova hypothesis. If LISA detects a merger with unusual spin characteristics hinting at exotic matter, while JWST spots a nearby gas cloud rich in unstable elements like curium, it would bolster the idea that quark-nova peppered the early universe with metals, jump-starting planet formation. Similarly, if Hyper-Kamiokande picks up a neutrino burst without a corresponding gravitational wave, it might signal a dark star's quiet collapse into a primordial planet, a process too gentle to shake spacetime but violent enough to flood the cosmos with particles. Critics argue this approach is like assembling a jigsaw puzzle with pieces from different boxes. The timelines might not align perfectly, but proponents counter that the mismatches themselves could be clues. A gravitational wave signal arriving late compared to neutrinos might reveal time dilation in the early universe, supporting Sean Carroll's theory of fractured cosmic timelines. Alternatively, JWST spotting metal-rich galaxies where LISA finds no black hole mergers could imply planets formed through quark-nova or dark matter-driven collapse, bypassing traditional pathways entirely. The 2030s will mark a paradigm shift, not just in data quantity but in interconnectedness. Projects like the Einstein Telescope, a next-generation gravitational wave detector, will join this network, while neutrino observatories like IceCube Gen 2 will expand the particle side of the equation. Together, they'll transform the question of planets or galaxies first, from philosophical speculation into a forensic investigation, with each messenger providing a piece of the timeline. What emerges may not be a simple answer, but a layered narrative one where planets didn't universally precede galaxies, but in certain pockets of the cosmos, they seized a head start, sculpting the universe in ways we're only beginning to imagine. If planets existed before galaxies, the implications for life's cosmic timeline aren't just scientific. They're philosophical, shaking the foundations of how we view our place in the universe. Consider Dr. Avi Loeb's provocative hypothesis. If rogue planets formed in the frigid darkness of the cosmic dawn, some might have retained heat from their violent birth or radioactive decay, creating subsurface oceans beneath layers of insulating hydrogen. In these lightless abysses, shielded from the deadly radiation of the first stars, life could have arisen not just earlier than we imagined, but under conditions we've never thought to look for. The math is startling. Even a modest geothermal gradient could keep water liquid for billions of years in a planet-sized ice shell. And without surface storms or seasons, these environments might be more stable than Earth. This flips the script on astrobiology's guiding principle, the habitable zone. We've long assumed life needs a star's warmth, but if free-floating planets nurtured life in their icy depths, then the universe's first organisms might have emerged in total darkness, sustained by chemistry alone. Loeb speculates that such life could have harnessed quantum tunneling in superconductive minerals to process energy, a biochemistry so alien we might not recognize it. The theological ripples are equally profound. If life existed 13 billion years ago, does that alter our narrative of cosmic purpose? Could these early, isolated biospheres have been sterilized by gamma-ray bursts, making humanity's existence not inevitable, but a stroke of luck in an ancient cycle of life and death? Theology and science collide here in unexpected ways. Some scholars of religion argue that a universe where life emerges repeatedly across time and space aligns with creation stories emphasizing abundance and recurrence, like Hindu cosmology's cyclical universes or the Kabbalistic concept of Shematot, where worlds are created and dissolved in divine rhythm. Others counter that Christianity's linear timeline, with humanity as a unique culmination, would face radical reinterpretation. Jesuit astronomer brother Guy Consolmagno frames it as a challenge to humility. If we find life predates galaxies, it's not our story being erased, it's our chapter being demoted from prologue to footnote. Yet the boldest implication isn't about life's past, it's about its future. If planets formed before galaxies, their extreme longevity suggests some might still harbor life today, frozen in cryptobiosis for eons, waiting for a chance encounter with a passing star to thaw their hidden oceans. Imagine a rogue planet, its biosphere dormant since the universe's first billion years, drifting into a modern solar system and awakening like a time capsule. This isn't just science fiction, it's a testable prediction. Missions like ESA's Comet Interceptor could one day rendezvous with an interstellar object and find it's not a rock, but a refugee from the cosmic dawn, its ice locking away the remnants of a lost genesis. The weight of these ideas transcends disciplines. A pre-galactic origin for planets wouldn't just rewrite textbooks, it would reframe our existential coordinates, suggesting that life, rather than being a latecomer to a galaxy-filled universe, might have been present at creation's doorstep, whispering in the dark long before the first sunrise. The search for the universe's first planets is about to leap forward with a new generation of telescopes, each designed to peel back cosmic history in ways we've only dreamed of. Leading the charge is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s with a single-minded mission to hunt rogue planets across the Milky Way and beyond. Unlike traditional planet searches that look for wobbling stars or transiting shadows, Roman will employ microlensing on an unprecedented scale, monitoring hundreds of millions of stars continuously for the telltale brightening caused by unseen worlds drifting through the void. But here's the game changer. Its wide-field infrared vision can detect objects as small as Mars floating untethered in interstellar space, some potentially so ancient their trajectories trace back to the cosmic dawn. Simulations suggest Roman could uncover thousands of these wanderers, and if even a handful exhibit strange orbits or metal-poor atmospheres, they might be relics from an era before galaxies finished assembling. Meanwhile, the Athena X-ray Observatory, slated for the 2030s, will tackle the mystery from an entirely different angle. While most telescopes study planets by reflected light, Athena specializes in detecting the faint X-ray glow emitted when rogue planets plow through dense gas clouds. As a free-floating world moves through interstellar space, it acts like a celestial snowplow, compressing hydrogen ahead of it until the gas heats up enough to emit X-rays. Athena's advanced spectrometers can read these emissions like cosmic tea leaves, revealing not just a planet's presence, but its composition and velocity. For primordial planets born before galaxies, the signature would be unmistakable, an X-ray aura showing pure hydrogen and helium without the heavier elements that only later supernova could produce. Even more intriguing, if one of these ancient worlds harbors a magnetic field, Athena might spot the telltale flicker of auroras wrapping its poles, ghostly northern lights powered not by a star, but by interactions with the galaxy's magnetic field. Then there's the Square Kilometre Array, or SCAR, the most ambitious radio telescope ever conceived. When its thousands of antennas spread across South Africa and Australia reach full power in the late 2030s, they'll perform a symphony of cosmic archaeology, tuning into the 21-centimeter radiation emitted by neutral hydrogen in the early universe. The magic lies in its resolution. SKA can map this primordial gas in 3 dimensions, spotting the subtle gravitational shadows where unseen objects bend space. A rogue planet from the cosmic dawn would leave a distinct fingerprint, a moving dip in the 21-centimeter signal, like a rock creating ripples in a stream. But SKA's real power comes from statistics. By surveying vast swaths of sky, it could reveal whether rogue planets cluster in patterns that match simulations of the early universe's structure. If they trace the filaments of the cosmic web rather than the later distributions of galaxies, it would be smoking gun evidence that planets predated galactic formation. What makes this trio of instruments revolutionary isn't just their individual capabilities, but how they'll work in concert. Roman will pinpoint rogue planet candidates across the sky. Athena can probe their atmospheres and magnetic fields, while SKA traces their gravitational influence on primordial gas. Together, they'll form an interlocking web of detection, allowing us to distinguish true cosmic relics from later ejecta. The data could settle once and for all whether planets were latecomers to the universe's grand design or its foundational architects. With each new observation window, we're not just building better telescopes, we're constructing time machines to witness the birth of worlds. So where does the evidence land in this cosmic courtroom? On one side, we have tantalizing clues, rogue planets with orbits that defy ejection models, simulations showing early gas could collapse directly into planet-sized clumps, and JWST surprise detections of mature galaxies that shouldn't exist so soon after the Big Bang. These threads weave together into a provocative picture, a universe where planets weren't just afterthoughts but pioneers, yet the skeptics wield sharp counterpoints. Without metals from supernova, how could true planets form? Why haven't we definitively spotted primordial free-floating worlds in the voids between galaxies? And could those anomalous rogue planets simply be outliers flung from later collisions? The James Webb Space Telescope may soon cut through this debate like a scalpel. Its next deep-field observations could uncover a smoking gun, a population of metal-poor planets drifting in pristine gas clouds untouched by later stellar generations. Even more compelling would be catching a protoplanet in the act, a dense Jupiter mass object caught mid-formation in a filament of the cosmic web far from any galaxy. Alternatively, JWST might silence the theory entirely by proving that all early rogue worlds bear the chemical fingerprints of later ejections, locking planets firmly into the post-galactic timeline. But let's suppose the pre-galactic planet hypothesis holds. What other cosmic truths might we have backwards? Could black holes, long assumed to form only from dead stars, have seeded directly from quantum fluctuations? Might dark matter's role be not just as cosmic scaffolding, but as an active participant in forging the first solid structures? Most provocatively, if planets came first, does that mean life's potential arose in the universe's cold, dark infancy, waiting billions of years for starlight to catch up? The beauty of this mystery is how it forces us to question the narratives we've etched in stone. Science progresses not just by finding answers, but by discovering how much we've misunderstood the questions. As JWST peers deeper into the cosmic dawn, we stand on the edge of rewriting not just a chapter, but the entire preface of our cosmic story. The universe, it seems, still has a few surprises left, and the next one might be hiding in the darkness before the first galaxies ever flickered to light.